Hello, everyone. Welcome to today's session of the Porous Media Tea Time Talk. My name is Marcel Mora, and I am joined here by Sarah Perez and our speakers for today, Yang Liu and Yang Meng. And this is section number 66, and we are quite happy. It's a milestone session. We have just reached 1,000 subscribers on YouTube. So that was, it doesn't sound much if you compare like with the big names on YouTube, but for us, a Porous Media channel by early career researchers, I think that's something to be a bit happy about. So thanks everyone for supporting the channel, and also especially thanks to Interpor that has helped us since the very beginning. So we are part of the Interpor Young Academy. And today, so let's go straight to the business. We'll start with the first talk by Liu Yang. And he is a PhD candidate at the Department of Engineering Mechanics at Tsinghua University. And his research focuses on theoretical modeling and numerical simulation of solid transport in both single-phase and two-phase flow through porous media. He primarily works on port network models and direct numerical simulations to study flow and transport processes, with particular focus on the upscaling of the relationship between the pore scale mechanisms and macroscopic behaviors. So, Yang, if you're ready,
Yes.
the floor is yours.
Yes. Okay. Thank you for your introduction. So, so nice to meet you, everyone. I'm Yang Liu from Tsinghua University. It's my pleasure here to share my recent work on porous media tea time talks. So the topic is scaling laws and mechanisms of hydrodynamic dispersion in porous media. So my presentation will go around the following four parts. Let's begin with the introduction. Solid transport through porous media is relevant across various applications, including the geological sequestration of carbon dioxide, the packed-bagged reactor in chemical engineering, and the contaminant hydrogeology. All these applications are closely related to the transport of solids. For example, the dissolved carbon dioxide, the chemical component, and the contaminant, and the porous materials, like the rock, like the packed-bagged reactor, and the soils. Hydrodynamic dispersion provides a macroscopic framework for describing solid transport by averaging the variations in both velocity and concentration. In this framework, the classical advection diffusion equation is reduced to the advection dispersion equation. And within this framework, the critical parameter is the dispersion coefficient, which characterizes the upscaling effect of the flow variations and the ability of a porous medium to disperse solids. However, porous media flow may exhibit variability at both intrapole level and interpole levels, as shown separately by the left figure and right figure, which together influence the dispersion coefficient. The intrapole flow variability is caused by the loosely boundary condition near the walls, and the complex pore geometries, resulting in larger velocity at the pore center and a smaller velocity near the walls. The interpole flow variability arises from the structural heterogeneity, causing the significant variations of flow characteristics across different pores, just as the right figure shows. As shown in the following figure, the dispersion coefficient exhibits diverse scaling behaviors to the Peckley number. The Peckley number quantifies the ratio of advection to diffusion. So among these diverse scaling behaviors, there is a power law regime with Peckley number spanning from 1 to 1,000. So the dispersion coefficient exhibits a superlinear power law scaling with respect to the Peckley number, and with further increase in Peckley number within the convective regime, the scaling transits to a linear form like this. So, however, the mechanisms over this superlinear power law and the linear scalings and over the transitions remain very limited. On the one hand, regarding the primary mechanism driving the power law regime, conflicting conclusions have been yielded over the mechanism, just as the following figure shows. Here, the superlinear power law scaling is indicated by the value of the curve, just like this, a value. In other words, if the curve decreases monotonically to a plateau like this, so then it will mean that the power law scaling is absent. Well, some studies have emphasized the critical role of interpol flow variability, just like the lab figure shows. Well, their results have shown that the superlinear power law, only occurs when the interpol flow variability is incorporated into the simulation. In contrast, some other studies have shown that even without the interpol flow variability, just as shown in the right figure, the power law scaling can still occur, provided that the structural disorder reaches a certain value. And on the other hand, none of the existing theoretic models can capture the transition from the power law scaling to linear scaling, just as shown by these equations. So these models express the dispersion coefficient as a sum of several as a sum of several different terms of packet number. So from these equations, so we can see that once a superlinear scaling is established, it will continue instead of transitioning to a linear form. So here we summarize that the contradictions in previous studies are attributed to the inconsistency in pore structures, just as shown in the following figure. So extensive pore structures have been adopted in previous studies, and here we show that the probability density distribution of velocities are significantly different for ordered structure and disordered structure, which will alter the relative contribution of interpol versus interpol flow variability and ultimately the scaling behavior. So here is a brief summary. There's low consensus regarding the scaling behaviors and the mechanisms over the hydrodynamic dispersion, and which is attributed to the inadequate consideration of interpol and interpol flow variability. And the motivation of this work is to fill this gap. Okay, so let's go to the second part. In this part, we will introduce a theoretical model for hydrodynamic dispersion in porous media. Well, first of all, we will do several simplifications to simplify the the transport of solutes is modeled as random walk of tracers, and the complex pore structure is reduced to a network of tubes like this. And in the model, we assume the redistribution of tracers at a load is proportional to the flux, which has two important aspects. For example, first of all, when tracers arrive at a load, they will select the downstream tubes with a probability proportional to the downstream flow rates. And on the other hand, when tracers enter a tube, they will select the radial the radial positions with the probability proportional to the flux as well. So in the random walk, the movement of tracers is modeled by spatial temporal transitions, and during each transition, the tracers will see a length of delta x and a time of delta t. So we assume these two random which are assumed to be two independent random and conform to these two functions. So the spatial and temporal coordinates of tracers are updated by this iteration. So this framework is equivalent to a continuous time random walk, and we can get the expression for the dispersion coefficient by this equation. So from this formula, we can see that the dispersion coefficient relies on the nature of the probability density function of transition times and the moments. So the critical point is how to obtain the formula for the probability density function of transition times. First of all, we consider the tracer transition through a single tube with the governing equation and the initial condition and the boundary conditions given as follows. Although this set of equations seems quite normal, an exact solution for the probability density function for transition time is unavailable. However, the transport can be divided into three distinct modes based on the following time scales. For example, including the advection time scale, the longitudinal diffusion time scale, and the radial diffusion time scale, and for which approximate solutions can be obtained for each mode. Here, the first mode occurs when the first mode occurs on the scenario where the advection time scale is far smaller than the radial diffusion time scale. So it means there is negligible axial or radial diffusion. So by very simple mathematical formula, we can get the local probability density function of the transition times like this, which scales as the t to the minus 3. The second mode occurs under the condition that the advection time scale is smaller than the longitudinal diffusion time, but larger than the radial one. So on this condition, so the solid transport result in tailored dispersion. So we can see that the tracer cloud move with the mean velocity. So the transition time is highly concentrated near the twice the advection time scale. And the third mode occurs when diffusion dominates over advection. So the transition time can be approximated by longitudinal diffusion time. So from this formula, we see that the local probability density function for transition time through a single tube is conditional on the advection time of tau. And the solutions for the first mode and the second mode is supported by numerical simulations with particle tracking. For example, at very high Peclet numbers, the local probability density function scales t to the minus 3 and match well with this analytical solution. And under moderate Peclet number, so the transition time distribution is highly concentrated near twice the advection time scale. So secondly, we examine tracer transitions across different tubes, and we made the following we assume that positive flow in each tube and a uniform longitudinal pressure gradient, and there are low dead ends. So based on this, we can obtain the formula for flow characteristics, including the flow rate, the velocity, the packet number, and the advection time scales. So from these equations, we see that the tube radius r exerts the most significant influence on flow. So here, it's reasonable to assume that the structural disorder is only caused by it arises only from the distribution of tube radius, and in previous studies, the process distribution for porous media are commonly modeled by Weibo or gamma distribution, and for smaller values of tube radius, the gamma and the Weibo distribution can be effectively modeled by power law distribution. So, however, we see that the hydrodynamic dispersion is basically shaped by the smaller pores. So here we adopt a power law function for the probability density function of pore sizes like this. And so we can obtain the probability density function for advection times. And as mentioned before, when tracers arrive at a pore load, it will select the downstream tubes with a probability proportional to the flow rate, like this. So we can obtain the probability for tracers selecting a conduit with advection time of tau is given by the flux-weighted probability density of tau, like this, which scales as tau to the minus theta minus 2, with tau varies from the minimum value to the maximum value, like this. So here we arrive at the global probability density function of tracer transition times, which is given by marginalization the joint probability density function like this here. However, please remember that the expression for the first term has three distinct modes corresponding to three distinct formula. So we have to take care of this marginalization. Okay, for a porous media, which is characterized by very strong interpol flow variability like this, with the advection time scale window is larger than 100. So maybe under different packet number, we can see different transition modes. For example, when the packet number is larger than the PEC1, so we can say all of the tubes are in mode 1. However, when the packet number is smaller than PEC2, so we can maybe see that different tubes have different transition modes. Okay, for porous media is characterized by very weak interpol flow variability. So we can see that all of the tubes are almost in mode 1. Okay, and for different scenarios, for example, when the advection time window is larger than 100 and with the theta value from 0 to 1, so we can see that the global probability density function, which is colored by red, is more or less the same as the flux-weighted PDF is similar to this one. Both of which scales as t to the minus theta minus 2. So this means the interpol flow variability dominates, while the otherwise when the window of advection time scale is is smaller than 100 or with the theta value, sorry, here is or with theta is larger than 1. So we will see that the particle transition time scales as t to the minus 3. So this is more or less similar to the local PDF of particle transition times. And here, so we can, so here we can get the moments of the transition time like this. And we find that the first moment of transition time is always scales as packet number as the packet number as the packet number. However, for different porous media, we can see different scaling behaviors as the transition the second moments like this. Okay, and by substituting the moments to this formula, so we can see different scaling behaviors for the dispersion coefficient to the packet number like this. So here we see that for a porous media characterized by the window of tau is larger than 100 and with theta from 0 to 1, we see a power law scaling. We see the scaling behavior from a superlinear power law to a linear and to the logarithm scaling. However, for other cases, we only see the logarithm scaling like this, and we said that the power law and the linear scaling is under the scenario where the interpol flow is significant. And the third part, we do some numerical simulations to validate the model prediction. Here we use 4 different tube networks like this. And for example, the order network, which is labeled as ON, which is exhibits very narrow window of tau. For example, from maybe 0.1 to 10. So it's smaller than 100. So this is an ordered network. While for other 3, for dn 0.5 to 1.1, so we see very wide distribution of tau like this, but they exhibit different values of theta. And here we do the open circles. The open circles represent the result by pore network simulation, and the field circle and the field symbols represent the theoretical model. And here we see that for dn 0.5 and 0.8, we see a superlinear power law to a linear one, and for the ordered network and the and the theta is larger than 1, we only see the logarithm scheming. And the final part is conclusion. Here, we develop a theoretical framework that captures the interplay between interpol and interpol flow variability. And our conclusions can be summarized as such a figure. So for porous media characterized by different probability density functions of advection times, we see different scaling behaviors between the dispersion coefficient to packet number. For example, for the window of tau is larger than 100 and with theta from 0 to 1, we see a superlinear power law to linear and finally to logarithm scaling. Otherwise, we only see the logarithm scaling. So yeah. So the work has been published on Journal of Fluid Mechanics. So you can find more more information on the paper. So yeah, that's all. Thank you.
Thank you very much, Yang. Very impressive piece of work. Like you did a lot. So we will open the floor for the questions. So for the audience online, please type your comments on YouTube if you have. And we will start with some in the studio here. Yeah, I think Marcel having a question. I do as well, but go for it.
Thanks, Sarah. So I was just wondering, you had like a radio distribution probability,
Yes.
radio probability distribution that was non-monotonic. It showed like a maximum at some particular radius, or a minimum maybe.
Do you mean
No,
this?
you mean a figure that you had like a long before, uh, like if you just like get back many slides, there were many there.
I
So there
think
is
this is
this,
with the Poiseuille flow, right?
yeah, and with the colors on the
Here?
radius there. No, back. It's really there,
This
for
one.
instance.
Okay.
So you have like a maximum probability at some characteristic radius there. Can you just tell me like where does that come from? Is it the linear and R cube term there? No.
Do you
You
mean
see
this
like
term?
no,
Do you mean this?
the green red green figure there, the circle with the probability distribution on the left of the tube there. No, yeah, there also you say selecting radio positions, and then you
Yeah,
have
yeah,
this.
yeah.
Why this particular distribution came up?
For example, okay, here we assume that when particle synapse when enter a node like this, a node, it will synapse the downstream tubes according to the flow rate. For example, here we have 3 unit flow rate and 2 and 1. So it will choose this tube with the most probability, right? Yeah. And when tracer enter a tube, it will select the radial positions with the probability proportional to the flux. Here, the
And
flux can be the flux can be like this: the velocity times the area here. So in the center, the flux is 0, and in the wall, the U is 0. So the flux is also 0. So it will reach the maximum here.
okay, super, thanks.
So, and this is the analytical solution for the probability density function along the radius, like this.
Mhm.
So we will see the maximum.
Right.
So
Thank you.
if we can stay on such a slide, for instance, so I will have a question about the calibration of your flux-weighted probability function. I am not sure to get where the weighting part comes from. Is it you weighting between the different modes?
No.
That-
The transition mode here we mode the transport as the spatial transitions. So so here the flux weight probability density function is the function of tau. Tau is the reaction time scale.
Yep.
So it means the time it takes for the fluid at the center of the tube to go through this tube like this.
Okay, so you mean you weight it based on the advection time?
So yeah, so this is the PDF for particles selecting a conduit tube like this.
Okay. All right, got it. And then, how do you think your probabilistic function will adapt to realistic pore geometries? For instance, if you include like Rossness tortuosities, would you change your probabilistic function, or do you just incorporate some geometrical insights into it?
Yes. So this is really a good question here. We assume that the structural disorder comes from only the tube radius. So this means we assume that the orientation of the tube is always the same here. So the beta, so the length, the tube length, and the angle of the tube center to the longitudinal is the same. So we only assume the structural disorder comes from the tube radius, like this. So I will show you the ideal case of our model. It's just like the DN 1.1, like this. we assume, yeah, it's a regular lattice with, but only the tube radius are randomly generated.
Okay. Yeah, cool. That's something to investigate, right? If you can just, because
Yeah.
I think seeing transport as a probabilistic function, do you think it will accelerate the upscaling of solute transport? And I have a feeling that it will. So, I mean, if you can adapt it to realistic geometries, and your approach is very interesting for upscaling purposes, right? Can you
Yes.
comment on this?
Yeah. So I think for more complex core geometries, maybe considering more complicated heterosity or like the topology. So maybe I think that so we will have to face the we will have to consider the problem. There are several random
Mhm.
so there are maybe several random factors like this here. Actually, the tube radius, the shape factor, the angle, and like something else. So maybe if these randoms are independent, so we can deal with it in a similar way. However, in
Yeah.
most cases, the tube radius and are correlated. Yeah. So maybe
Okay.
so this may be very very. So I think this is the most significant thing.
Competency, yeah, okay,
Yeah.
that will affect your flow. Okay, cool. Thank you very much, Jan. I don't see any question from the audience. Marcel, do you have one more? Or can we move to the second speaker?
Okay, thank you.
So thank you very much again, Yang, for your presentation. We will now move to our second speaker of the day, which is Yang Meng. He did his undergraduate at China University of Petroleum in Beijing, studying petroleum engineering, and then he studied applied computational science and engineering at Imperial College London. And Yang Meng is now a PhD student in HKPolyU University, working on computer sciences and super resolution techniques. And today he will give us insights into super resolution beyond instrument limitation for carbonate rock imaging. So thanks again for joining us, Yang, and the floor is yours.
Thank you so much for the introduction. And today I'm going to share a topic I just did in the POR 2024. The topic is super resolution carbonic rock images and beyond the instrument limitations. And I will briefly talk about the background of this research, and then talk about the purpose again, which is our model we prefer to mention. And after that, I will share some results and analyze. And after that, I will take a brief summary, and hope you can have something take away after this presentation. And the motivation of this research is the trade-off of always exists in the FOV and the resolution. What is FOV? FOV is called field of view. So, for example, if you have a camera and closer to the objects you want to observe, you will have a smaller FOV, but you can have a higher resolution, which means you can see the details of the object more clear. But on the contrary, if you want to look at the overall of this object, you will definitely will lose the resolution. So the resolution and FOV, this trade-off is always exists. So, but what if we want to overcome this trade-off, and especially when we studying the mechanism of the especially the cross-resolution fluid flow in porous media. And actually, the equipment upgrade very fast, but it's not what I want to share today. I'd like to share how can we use the deep learning technology to do this task. Artificial intelligence is actually on replicating human intelligence with the mathematical method, and the key problem is to find the relationship between the input and output data. So in this task, what is our input and output? So now we can fix the FOV, fix the field of view. So in the image on the right, on the left and the right, you can see the same thing, but they have different resolution. And we can do right now is to use the deep learning algorithm to bridge to bridge the gap between the low resolution image and the higher resolution images, which means we can use the lower resolution image to create the same OV but higher resolution images. This is our task. And in this research, we include two data sets, and you can, as for the first data set, you can simply search the MRCCM on the Google, for example. You can easily find it. And another data set is scanned by ourselves by Shenzhen University. The name is called Porous scan. You can just we have open sources. You can just see it on the web search. Okay, let's talk about the detail of this data set. In the XY panel, actually, you can see there is a blue window and a red window. Actually, this is on the XY panel of the macro CT scans. And as for the first data set, this image is on the XY panel is slightly huge. So we can use we actually separate the each slice in XY panel, which means along the z-axis, into 16 sub images for training. Smaller images is easier for training. And as for the second data set, and many thanks to the Shenzhen University provides the equipment for the macro CT scan, and they can scan the same carbonate rocks more than one times with different resolution, and the resolution range is from 1 micrometer to 30 micrometer per pixel. So we scan three across three resolution images from 16 to 4, and the highest resolution is 1 micrometer per pixel. I will show you why we scan the 1 micrometer per pixel later, and we use the 16 and 4 micrometer per pixel images to prepare the paired data set. So this is the second data set, and here it shows the macro CT scans the 3D volume. And another tricky I want to mention. As for the second data set is actually the XY panel is not very huge, so we are not separate the sub images. We just use the original XY panel for training. And another tips is if we use all the images in the high resolution image, lower resolution images, and we need to sample the high resolution images every 4 slides to get the paired data size. Okay. After we talk about the data set, let's talk about the neural networks behind to bridge these gaps. And many thanks to the NTIRE. This is actually a computation in computer vision, and they provide many open source network architectures and suitable for the super resolution tasks. And the super resolution has been successfully tested on their architectures have been tested on many general images datasets. And in the super resolution generator part, after testing and the experience, we can simply separate the generator into 3 parts. the first convolution part called the shallow feature extraction part, and then there is a deep feature extraction part, and there's a repeat many neural networks like the CNN or Seven transformer in the next architecture, and after that use the upsample. There's upsample layer, and after upsample there we need to add 1 to 3 3 layers of convolutional layer to activate the final image, and so this is the common structure, which is shallow feature extraction, deep feature extraction, and the upsample part. Because only after the upsample we can achieve the resolution. We can change the resolution. So after the operation we mentioned previously, on the left we have the lower resolution volumes, and after training this model and feed the volumes into the neural networks, we can generate the image like in the middle part. And actually in the middle part the z-axis is actually zipped, because we are just train the XY panel, and we just training the z-axis is only 1, so the z-axis will not change. So how to achieve the real 3D super resolution? We have 2 strategies. The first one is very easy to achieve. We can use the tools like ImageG to just using the bicubic interpolation and only on the z-axis, so you can create the real 3D reconstruction. And another to achieve higher reliability, after the interpolation, we also trained a smaller super resolution model to map the relationship on the YZ panel or XZ panel to the ground truth. Actually, in the second part, our model is not. It shouldn't be called a super resolution model. It's actually a denoising model, because the resolution is actually kept still. Okay, after the architecture, let's talk about the computational cost. While training this kind of model, we will achieve 4 times the resolution increase. The parameter takes about 5 million, and usually takes the GPU 6 to 8 GB data GPU memory, and using a single 4090 GPU training for 24 hours is enough. And as for the inference for the single image is very fast, because this is a 2D model. In the traditional convolutional neural network, it takes about 10 milliseconds on a single 4090 GPU, and as for the swing transformer architecture, it will be slower. It's about 100 milliseconds a single 4090, and we also test how the time consuming while constructing a 3D volume, and takes about 600 and 1200 as output, and this is the input, and after reconstructing this 3D volume, it takes about 3 minutes. It's really fast actually, and after actually the nature of the 3D CT macro CT is actually naturally a 3D model. So why not we use the 3D super resolution model, but we use the dual 2D model just like that? Why not? Why we use the dual 2D model? We have many concerns. The first thing is the model complexity. need to correspond to the size of the model parameters and the size of the data set. So these three parameters should increase at the same time, and most of the time, the data set probably is not huge to train the 3D model, and the 2D model is easier to convert. And the second concern is the translation invariance of CNN architecture. So what is the translation invariance? For example, while training, we can separate the image into a very small size as the input. And while inference, we can feed the very huge image as the input. So the CNN can be used to consistent reconstruction of a large field of view images. So at any size through the location-free learning. Actually, so the CNN is actually a location-free. So that's why it works for that's why we train the Dual 2D model, because we can feed the very huge input and create extremely huge output, so that after slicing by slicing generation, we can finally create a very huge 3D volumes. This is the validation study on the first data set. And we use the bicubic interpolation and also 4 different the super resolution architectures. The super resolution architectures performs very well in the first data set. And we also tested many 4 parameters in the computer vision. The first 2 parameters is the larger the better, and the second the last 2 parameter is the lower the better, and the super resolution architecture output performs much better than the bicubic strategy, even though the bicubic is very fast. And we also did the validation study on the second data set. And you probably can notice sorry, I need to introduce this 4 model. The EDSR is actually is a fully convolutional neural network, and the ESR GAN is a similar structure to the EDSR, but have a GAN loss. GAN is generative adversarial networks with a GAN loss, and the swing AR is based on a swing transformer architecture and only the generator. And the swing AR GAN is actually the only difference is we add the GAN loss, adversarial loss, and we can notice the GAN loss can increase the model stability, especially on the challenging data set, even though this difference is smaller in the first data set. Also, the swing transformer architecture in the rightmost 2 images, the output, you can notice that it performs more stable on the complex data set. And after the computer vision validation, we also did some physical parameters evaluation. And so we need to do the image segmentation, and for every digital rock, we need to train a specific model, or we need to train a specific segmentation model, and we are also using the CNN-based model and train for each digital rock. And this is the validation. This is a validation, and we evaluate the 3 parameters we probably concern. The first is paucity. Second is Euler's number. Euler's number is to study the connectivity of the pores, and the last one called specific surface area is the surface. It is the surface of the digital rock and the pore. over the volume of the digital rock. And after the validation study, how can we beyond the detection limitation? This is we care more about. And currently, we have already trained a model that input low resolution images and use a deep learning model to predict the higher resolution images. And now we have the 16 and the 4, and how can we predict the resolution at 1 micrometer per pixels? Here we provide two strategies. The first one is we only use the low resolution images, and we can feed the low resolution images into the model twice, which means we can feed this image into the model and get the output, and then feed the output into the model again, and we can receive 1 micrometer per pixel images. Because in the super resolution architecture, there's a upsample structure. I just mentioned. Sorry, here is upsample strategy, upsample architecture inside the generator inside the generator. Another strategy is actually we already have the higher resolution images. This is the ground truth, and we can feed the higher resolution images as the input of the model. Actually, it is not allowed because we are training the relationship between the lower resolution to higher resolution images. The input should be lower resolution images, but we have tried. What if we feed the higher resolution image into the model? What will happen? This is the result shown, and after generate the very extremely high resolution images, and we did the macro digital rock reconstruction and the segmentation and evaluate the parameters. And you probably noticed especially in the OLS number part, the swing AR model without GAN loss performs not very well, and actually it's similar to the lower resolution and the different strategy. And the second strategy is feed the higher resolution image into the model, and this part is my AR strategy too, and similar to the HR image. HR is actually the input. It's similar. So this is input and this is the output. The input and the output is actually similar, but different from the ground truth. But using the SMAR GAN can stably predict these three parameters, even though it's not 100% correct, but performs much better than the SMAR model without a GAN. So I guess you still remember the first data set. We have only two different resolutions. If we use the strategy I just mentioned, we use the LR images to feed into the model twice, or HR image feed into the model once. We can generate the extremely high resolution images. But because we have only two resolutions, we cannot justify the correctness. It seems we cannot justify. So we don't have the labels. So we use the downsample strategy to on these extremely high images, and come back to the HR ground truth. And until now, you probably find something weird because we have two different resolutions, and we use the upsample strategy and then downsample. It seems we did nothing and come back to the HR ground truth. But something interesting in this research is after downsample, no matter which strategy, SMAR or ESR GAN, no matter which strategy, the physical related parameter is actually it should be equal to the HR ground truth, right? But the positive is actually related to it, not huge difference. But the Euler's number and the specific surface area changes so much, and the Euler's number increases about 15%. And 15% is not really huge, but the x-axis is actually the log axis, so the increase is actually really huge. And the specific surface area is actually the same way. Okay, let's come back to this image. Because in our data set we have scanned 3 different resolutions, IR, HR, and this is 1 micrometer per pixel, extremely high resolutions. You can notice the different parameter will the size of the parameter will increase during the resolution increase, which means if we have a rather higher resolution, we can find more mini pores or nanopores, nanometer scale pores, so which will increase the porosity. And the Euler's number is similar, and more mini pores will be connected together, and the algorithm will detect them. So the Euler's number will increase, and increase significantly from the high to extremely high. Also, the specific surface area, it will increase through the resolution changes. So this is our finding. It seems so what's the meaning of this finding? For example, if we currently have only we can scan relatively high images, we can improve the quality of the image without using higher resolution instruments. And we can just use this data. We can just use this image and feed into the model, and then use a downsample strategy and come back. And it seems we did nothing. We did nothing only on the resolutions, but the SR model can predict what will happen in the higher resolutions, and in the downsample strategy, it will keep in the images. So that's why we can keep the resolution scale and get higher quality images. And there's a summary and takeaway. The first is the super resolution technology can effectively balance the contradiction between the FOV and the resolution, especially in the cross-resolution study. The second is we use the dual 2D SR strategy, and it can help us to get the continuous images with a huge field of view. The third one is the 2D models are easier to converge and friendly to smaller data sets. The fourth one is the SR model can be used to predict images beyond the resolution detection limitation of the instruments. We have already tested both the image level and the physical level. The fifth one is the downsample strategy can help improve the image quality while maintaining the resolution scale. I just mentioned we don't need the higher resolutions, but we can improve the image quality. Okay. And there's the last tip is realistic application tips. Actually, in the real world application, we cannot scan the digital rock for 2 times and train the model and predict. We usually scan only once. How can we use the supervised model, which means we need low resolution and high resolution pairs? We can just use a downsample strategy. For example, we can scan the high resolution images and then downsample to create the low resolution images and get paired and train the relationship and feed the high resolution images, the ground truth, into the model to predict the preceding word. And many thanks to my current supervisor, Zhang Xingchen at EIT after graduate from Imperial College. And a special thanks to Tsinghua, who is my senior at Imperial College, and currently he has already back to China and create a team in Shenzhen University and get very well equipped. And many thanks to the idea and equipment he provided. And the special thanks to the Kunnian Tang, who is actually not study, but research fellow at University of New South Wales, and he provides the MRCSM data set and also some inspirations. And there's an advertisement for the Professor Tsinghua, and many thanks to his equipment. And I guess his equipment must be top tiered in the world, I guess. And thank you so much for the invitation of the Interpol. Okay, that's all.
Thank you very much, Yang, for the very interesting presentation. Again, I encourage the audience online to ask questions on YouTube, and we will start with you from the studio. So, Marcel, do you have any questions?
Yeah, I have a quick one. So thanks a lot. It was very interesting. So if I understood correctly, so your different models, you don't have like a universal answer, like this is the one best model that works for any situation, right? Like the different parameters. Sometimes like one model, for instance, for the porosity here, it seems that the SIG2 model was best, but then if you want like a specific surface area, sometimes another model was best. So could you just comment on that? Like if someone knows that, okay, I'm going to do a simulation of, I don't know, some reaction flow, so specific surface area is very, very important. And then would this person like go for one particular model instead of another? Is this the way to think about it?
Yeah, actually we have, we just, actually I mentioned four different models. I will use this image. The first image is using the generator only. The second one is using RDB generator and plus the GAN loss. And the third model is use a swing transformer architecture only. And the fourth model is use with architecture plus the Beijing 19, the GAN loss. We have four different models, but after testing, the swing AR GAN model is here. Is the last one, swing AR GAN. Is using the swing transformer architecture as a generator and using the Beijing 19 as the discriminator for training, and this model performs most stable and easy converge.
Yeah, I would have a question about this model, to be fair. So this swing transformer, from what I understood, is kind of greedy in training data sets. So do you use exactly the same amount of training images for the four models? And can you comment about the computational cost of training each different models?
Sorry.
So from what I understood, the swing transformers are kind of greedy in the number of training images you need.
Sorry, I'm slightly not really understand it.
Okay. I mean, transformers are known to require a lot of images for training. Yeah. So my question is, did you use exactly the same amount of training data sets for both models? And can you comment on the computational cost of training? I mean, following the question of Marcel on which one we would use. I mean,
so about the data set size, right? Because I just mentioned here. Sorry, just mentioned somewhere. yes, here. The model complexity and the model parameters and the data set, right? So there's 3 different parameters, and this parameters actually we use in the training. So while we choose the data set and the model parameters, we need to firstly consider the problem complexity. Actually, here is a problem complexity. Sorry, it's spelled incorrect. So if the problem is very complex, we probably need a high. We probably need a larger parameters and a larger data set. And for the data set we provide here, the first data set is actually very easy to converge, and the data set is very we can create it very huge. And we actually the smallest data set that makes the first problem converge is actually a few thousand is enough, but we actually use about 3 for training only use over 30,000. Actually, a few thousand is enough. And for the second data set is slightly different. It's slightly harder to converge, and also we have actually only 3 because we are slicing on the z-axis, right? The XY panel. We have only 300 paired of images for training, right? This is actually not enough for training a stable model. But we can use some strategies like the slicing. After slicing the image, we can use the mirror this related technology to expand the data set. And in the second data set, we actually using also a few thousand paired of images. It will make the model stable converge.
Okay, good, thank you. And then I will have another question on your physical parameters evaluation when you try to get like the porosity specific surface area. I have a feeling that like the parameters that have 3D influence like the specific surface area mostly underestimated or not very well catched with our models. So do you think it comes from the fact that you consider a 2D network rather than a 3D one? Or do you have any insights why you have such difficulties in catching these parameters?
Actually, if we want to as for the positive, we can actually calculate on the 2D images. It's okay, but the Euler's number and the specific surface area, it must be operated on the 3D models. And so how can we do that? Is to choose. Now we have a SR models, and we can create 3D volumes and with higher resolutions and generated by AI, right? And we can train the segmentation model and segment the images one by one. And after segmentation, and we need to reconstruct. You can see the image on the right.
Okay.
After
so it's a
and we can calculate.
All right. Thank you. So it's a post-processing step for these parameters. All right, got it. Thank you very much. So we have a comment from Daniel Han, which is just saying great job. I think we agree on this. So thank you again, Yang, for your nice presentation today. And I think we will, if there is no more question from us, we will finish here. So the other speakers had to leave, but thanks again to both of you for joining us. Very interesting session. And we would like to advertise our next month session, which will be on the 11th of March. And we'll feature Matmat Masouminia from McMaster University and Reza Hagani from Polar in Norway. Yep, so this is us. If you have any comments, want to be involved as speakers, or just subscribe to our mailing list, feel free to reach the Porous Media Tea Time Talk team at our Gmail address there. And yeah, thank you once again to the audience for joining us today, and stay tuned for the next sessions of the Tea Time Talk. Bye, everyone.